We're looking at section 5.1, working with radicals. So the first thing I want to show you is what a mixed radical looks like. So it is the product of a monomial and a radical. A monomial means number, so here's the monomial. And the radical is everything that's underneath that square root, or in this case, cube root sign. Okay, so that is a mixed radical. Within that, there's a couple of different terms. The number in front, this -8, is called the coefficient. So it tells you it's cube root or square root, and if there's nothing here, you assume it's square root. That's called the index. This is the radical sign, that little house is the radical sign. And underneath the house is called the radicand. So it's going to be times when the workbook asks you certain things about indices, or they ask you about coefficients. And if you're not sure, just turn back to this page 188 because they'll show you. Okay, another definition is an entire radical. An entire radical means that we don't want any coefficient in front. We don't want this -8. All we can have in front is a -1 or a 1. Okay, so in order to convert to an entire radical, we have to somehow put this -8 back in, or an 8 back in. And what we're going to do to do that is we're going to look at this table of squares, cubes, and perfect fourths. So we're looking at the number 8 is outside, and it's cube root, so we're looking at cubes. And 8 cubed is 512. So in order to bring that 8 back in, we have to cube it. So it's 512. The cube root of 512, and we'll leave that negative sign out, is the same as 8, and then we have that multiplied by the cube root of 45. Now, because both of these have the same index, we can combine them. So we can say this is equal to negative the cube root of 512 times 45. And so we'd get out our calculator, 512 times 45, 512 times 45, and we would get, here we go, negative the cube root of 2, I can't remember that number, 230. Okay, so now we just converted this mixed radical right here into an entire radical. Okay, radicals are called like radicals when they have the same index and the same radicand. And the example that they gave for that was 9 root 2 and -5 root 2. They are like because they have the same index. So here there's an imaginary 2. There's an imaginary 2 there. It's like square root, and the same radicand. And when we have like radicals, we can add and subtract them. So if I have 9 root 2's minus 5 root 2's, well, I'm left with only 4 root 2's. I can combine those. Okay? Simplest form, a radical in simplest form, means that we want to simplify it. We want to put it in the simplest form. So the radicand does not have a fraction, the radicand does not contain a factor, and then denominator does not contain a radical. The example they gave there is the square root of 20. Well, that can be simplified to the square root of 4 times 5. And we chose 4 very carefully. 4 appears is a perfect square, and the square root of 4 is 2. So we did choose that one very carefully. Oops. So we can take the square root of 4, which is 2, we put it outside 2 root 5. Now this radical is in its simplest form. Okay, so what we're going to have to look at throughout these is comparing and ordering radicals. We're going to look at adding and subtracting, and also restrictions, because there's some values that just don't make sense when we're working with radicals. But I think what we'll do is we'll dive right in. It says expressed each mixed as an entire. Remember, look back to page 188. Entire means that the radical can only have a coefficient of 1 or -1. In other words, we're putting this 5 back under the radical sign. So we have 5 root 3. Well, we need to rewrite 5. 5 can be written as the square root of something. So 5 is the square root of 25. So we're going to write this as the square root of 25. Now, because these have the same index, we can rewrite this as the square root of 25 times 3, which is equal to the square root of 75. So we have changed this mixed radical into an entire radical. Okay? State the restrictions. That doesn't, because we're dealing with real numbers, doesn't really apply here. Okay? Let's try B. So B is 2b, or not 2b, times the square root of b. So we're trying to put this entire thing back under the radical sign. Well, the number 2 can be written as the square root of 4. B can be written as the square root of b squared, and we're timesing that all by b. Okay. Next we're going to combine these together, so we're going to get the square root of 4, and we have b squared times b, so that is b cubed. Now this is a case we have to look at restrictions. So are there numbers of b that would not make sense? That if we put it in here would give us something that we don't know how to handle. Okay, and if you look back on page 189, it says restrictions. The denominator cannot be equal to 0. There's no denominator here. If the index is even, the radicand must be positive. So this index, remember when there's nothing here, we assume it's a square root, so the index is 2. This is an even index. So we cannot have a negative number. We do not know what the square root of a negative number is. So in this case, if b was a negative number, for instance, if it was -1 cubed, we would get a negative answer. So in this case, b must be greater than 0. b cannot be negative. So that's the restriction when you answer this question that you would have to add on. Okay? Question C is very similar to that, so we're going to move on to our next question. So now we're working backwards. We're going to express each entire radical as a mixed radical in simplest form. So now we want to simplify these. So this is the square root of 192. What we're going to look for is we're going to look for the biggest perfect square that divides evenly into 192. So we're looking back to this table. What does 192, what is it divisible by? So let's get out our calculator. So 192, is that divisible by 4? Yes, okay. But we want to see if there's anything bigger. 192, is that divisible by 9? Nope. 192, is that divisible by 16? Oh, it is. Very nice. Well, I know 192 is not going to be divisible by 25. Let's try 192 divisible by 36. Nope. 192 divisible by 49. Nope. And 192 divisible by 64. Ooh, 64. And since I'm only left with 3, I know nothing bigger should be able to go in. So 64 and 3. So I'm going to rewrite 194 as the square root of 64 times 3. Now the square root of 64, looking back at our table, the square root of 64 was just 8. So I'm going to write this as 8 times the square root of 3. Okay? There's another way we could have done this that the textbook goes through, and that's showing prime factorization. Prime numbers are numbers that can no longer be divisible by anything else. So they're saying we're going to rewrite 192. I'm going to erase this. They're going to rewrite 192 as the square as 2 times 2 times 2 times 2. 6 2s. 1, 2, 3, 4, 5, 6 times 3. And how they did that is they also just took their calculator. Oops. They just took their calculator and they said 92 divided by 2. Oops. 192 divided by 2. So they said 1, 2, 3, 4, 5. They said, oh, look, I got 6 2s and then a 3 was left. So that's how they did that. And now they said, well, look, here is a perfect square, 2 times 2. Here is a perfect square, and there is a perfect square. So there was 2, 4, there was 3 2s, so they said 2 to the 3 out here times 3, and that is just 8 root 3.